It's now time to simulate the performance of this chassis frame under loading conditions using SOLIDWORKS simulation. Under the SOLIDWORKS add-ins tab, you can quickly toggle simulation on, or alternatively navigate to Tools, Add-ins and enable simulation under the Active Add-ins column. Switching to the Simulation tab in the Command Manager, we can now create new studies. Testing the torsional rigidity is one of the crucial benchmarks for any chassis, and a number of studies have been set up in advance, with a partially complete study that we will review to highlight some of the best practices. Using the weldment tools in Phase 2 means that the body geometry is automatically imported and converted to optimized 1D beam elements in simulation, which are specifically formulated to handle beam bending, tension, compression and torsion. Cross-sectional tube properties are pulled directly from the SOLIDWORKS model, so we don't need to worry about inputting this data. We can easily right-click on the chassis part in the tree and apply a material to all bodies. These bodies are organised into a cut list, but this can be deleted to see a full list of weldment bodies. Any smaller bodies that are not load-bearing have been excluded from the analysis using the context menu options, but we can include these again if required. The beam joints option allows us to automatically calculate beam connection points and add additional new beams to the design if updates are made. Small gaps between non-touching members can also be considered as joined by specifying a tolerance. An important option to enable is to keep modified joint on update so that individual beam members between multiple chassis design iterations can be compared directly. Beams are assigned a number that can be referenced when outputting results. Turning this option off will mean that each beam will be reassigned a new number if the joints are recalculated, meaning beam 1 in the first iteration of a design may not be the same beam in the second iteration. Hence, leave this option enabled. The visibility of all simulation symbols can also be toggled from the heads-up toolbar, which is useful when reviewing a setup. This chassis is assumed to be welded together, so the only connection between the geometry is a global bonded contact, which should be the default connection in the model. Any contact sets added to the model can override the global contact and would potentially be required for a chassis that was fixed together or assembled using fasteners. We can use the Fixtures Advisor to guide us through adding some constraints to simulate a torsional test case where some suspension nodes are instantaneously fixed in space and a load is applied on opposing suspension nodes, simulating a speed bump impact scenario or cornering loads in a quasi-static analysis. In this case, we will use a powerful feature called reference geometry and independently control degrees of freedom at the suspension nodes. We'll start by picking the floor as the reference plane and then pick 4 rear suspension mounting points and stop any translation in the X, Y and Z directions but allow rotational degrees of freedom. However, we are analysing the full chassis so we can edit the fixture and also constrain the suspension nodes on the rear left side of the chassis. And we can also increase the symbol size to make this clearer in the viewport and for any simulation report images. The next stage is to apply the forces on the front suspension mounting points in equal but opposite directions to simulate a twisting motion about the chassis centerline. We pick the beam joints option under the selection heading, reference plane, and then apply 300 newtons of loading normal to the plane to apply a vertical force on each of the front mounting points on the right side of the chassis. We can then repeat this process but flip the loading direction on the front left mounting points. We'll add gravity to consider the self-weight of the vehicle, and we are now ready to mesh. Beam structures are incredibly lightweight and quick to solve, so meshing using this technique, a number of connected beam elements can be created in just a few seconds, which represent the frame geometry using tubular members. If the weldment beams are of different cross-sectional shape, you can right-click and render beam profiles in 3D. However, this is purely visual and does not affect the calculation. Right-clicking at the top level of the simulation tree and navigating to Properties allows us to set some simulation options, including the automatic solver selection, as well as manage where the results are stored. Running this study takes just a few seconds and we are presented with stress and displacement results. We'll switch to another study to look at how we can post-process results to extract the required information easily. We can edit the stress plot in this model and adjust the legend units, stress type such as axial, bending and shear, and set a custom deformation scale. Other useful options to toggle are under the Chart Options tab, where minimum and maximum values can be displayed in the viewport, and number formatting can be adjusted to floating. The boundary options on the Settings tab also control outlines and other useful overlay settings to superimpose the model on the original undeformed shape. We can animate the motion to view the distribution of stresses in the frame members, in this case around 50 megapascals, as well as displacement plots in the global Y direction, which shows vertical deflection of the frame. Notice the deflection downwards of 1.6 mm is actually the larger of the two displacement values. We can also manually probe areas of interest on the mesh to extract the stress at the bottom 4 corners to check the values are of similar magnitude, or add and remove additional measurement points if required. The summary provides useful tabulated data that can be saved out to a spreadsheet file or plotted graphically. A similar setup has been created to test the torsional rigidity further by fixing the front suspension mounting points and applying a force to the rear suspension nodes. We can see the maximum stress is slightly higher when considering this case, but still comparable, and the distribution of stresses through the engine support members is more evident. As before, we can animate the displacement in the rear bulkhead and engine cradle members. Extracting forces in individual beam members is extremely easy. Right-clicking on the results folder, we can choose to list beam forces or stresses. We can then toggle the range of beam elements to analyze. There are 116 members in this model, and the beam number is related to the Keep Modified Joint on Update setting mentioned earlier. Once we accept this, we are presented with a table of force components and values for each beam and its individual mesh elements. Clicking beam 1 will highlight it in the viewport, and working our way down the columns, we can see the forces in each beam cell of the first beam member. This is a lot of data which might not be required, so we can toggle to only show extreme, maximum and minimum values at any cell along each beam. We are interested at joint forces, so we'll choose to only show the beam start and end points indicated by the red and blue spheres. We can move through each beam member to see the values and location of the beam, either by clicking it in the row or using the navigation buttons in the window.